The asteroid belt is a region of space between Mars and Jupiter filled with rocky and metallic material left over from when the solar system formed. It exists in that specific location because Jupiter's gravity kept disturbing the material there, so it never came together into a planet. This matters because most people carry around a wrong picture of what this region actually looks like, and that wrong picture shows up whenever they see a headline about asteroid mining, a space movie, or a news story about an object passing near Earth. You're about to get the version that's actually correct. This is the important part to hold on to as you go through everything else. Almost every wrong idea people have about the asteroid belt comes back to one thing: misjudging the actual scale of the space involved. Once that one thing is fixed, the rest of this topic falls into place quickly. Let's start with what the belt actually is. It's a wide, ring-shaped region orbiting the Sun, sitting between the orbit of Mars and the orbit of Jupiter, made up of chunks of rock and metal of every size. This matters because most people picture something completely different from reality, usually shaped by science fiction. Think about a shipping yard full of containers. If you only saw a movie version of that yard, you'd expect containers stacked wall to wall with no gaps. If you walked in and saw the containers spread out with wide gaps between them, you might assume something was wrong when in fact that's simply how the yard is laid out. The asteroid belt works the same way. It's a real region with real material in it, but the spacing is nothing like what fiction shows you. In plain terms, the asteroid belt is a wide ring of scattered rock and metal orbiting the Sun between Mars and Jupiter. Now let's look at why it formed there in the first place. Early in the history of the solar system, the material in this region never clumped together into a single planet. This matters because it explains why this specific stretch of space is full of debris instead of holding one solid world the way other regions do. Picture a construction site where a crew keeps trying to pour and set a foundation, but every time they get partway through, a piece of equipment shows up and disrupts the site before the concrete can cure. The section never gets built. It stays a pile of separate materials instead of becoming a finished structure. That's what happened in this region of space. The material was there, but it never had the chance to finish coming together. Put simply, the belt exists because the material that could have formed a planet was never allowed to finish combining. The reason it was never allowed to finish combining is Jupiter. Jupiter's gravity is enormous, and its pull kept reaching into this region and disturbing the orbits of the smaller objects there. This matters because it shows how one large, dominant force nearby can permanently change the outcome for everything around it, even if that force never touches the material directly. Picture a large stamping machine running on a factory floor. Every time it cycles, it sends vibration through the floor. If you tried to assemble a set of small precision parts on a table near that machine, the vibration would keep shaking the parts out of alignment before you could bolt them together. You wouldn't need the machine to touch your table for it to ruin the assembly. Jupiter did the same thing to the asteroid belt across billions of years. In plain terms, Jupiter's gravity repeatedly disrupted the material in the belt, which is why it never formed into a planet. Next is the size range you're actually dealing with. The objects in the belt range from dust-sized grains all the way up to Ceres, which is large enough to be classified as a dwarf planet. This matters because the word asteroid makes people picture one uniform size, when the reality spans an enormous range. Picture a scrapyard that takes in everything from loose metal shavings swept off a shop floor to entire car frames dropped off by a tow truck. Both are scrap metal, but treating them as the same thing would be a mistake in any practical sense, whether you're sorting it, weighing it, or pricing it. The asteroid belt is the same way. Some objects are barely bigger than a grain of sand, and others are hundreds of miles across. Stated plainly, the belt contains objects of vastly different sizes, from tiny dust grains up to a dwarf planet. Here's what's actually happening with the spacing, because this is where most people's mental picture breaks down completely. The objects in the belt are typically hundreds of thousands of miles apart from each other. This matters because it directly corrects the crowded, chaotic image most people have from film and television. Picture the open ocean with a handful of buoys marking shipping lanes. Even though the ocean is enormous and the buoys are real, spread out that far apart, you could sail for a long time without getting anywhere near one. Nobody would describe that ocean as an obstacle course. The asteroid belt is spread out on a similar scale. It is not a field you'd have to dodge through. This is also why every real spacecraft that has flown through the belt has done so without needing to steer around a wall of debris. Engineers plan the route the same way a ship's crew would plan a course through open water with a few known markers, checking positions in advance rather than reacting to obstacles in real time. In plain language, the objects in the asteroid belt are spaced so far apart that the region is mostly empty space, not a crowded obstacle field. The next concept is motion. Every object in the belt follows its own elliptical path around the sun at its own speed, based on its own distance and orbit. This matters because it corrects another common assumption, which is that the belt sits still like a ring drawn on a diagram. Picture a wide highway with several lanes where every car is in its own lane, moving at its own speed, based on how that particular lane curves and where that driver is headed. None of the cars are parked. They are all independently moving through the same general stretch of road at the same time. The objects in the asteroid belt behave the same way. Every single one is in motion, all the time, along its own path. Stated simply, every object in the belt is constantly moving along its own independent orbit, not sitting fixed in place. Composition is the next concept, and it matters just as much as size or spacing. Asteroids are made of different materials depending on where in the belt they originally formed, and those materials generally fall into rocky, metallic, and carbon-rich types. This matters because it determines what an asteroid is actually worth, scientifically or economically, and what kind of equipment would be needed to work with it. Picture a construction materials supplier with several piles on the lot. One pile is loose gravel, another is stacked structural steel beams, and another is bagged concrete mix. All three piles are construction material, but you would never use them interchangeably, and you would never price them the same way. Asteroids work the same way. A rocky asteroid, a metallic asteroid, and a carbon-rich asteroid are different resources with different value and different handling requirements. This is also why a company evaluating an asteroid for mining spends real time and money confirming which type they're dealing with before committing to a mission. The same way a buyer would confirm what's actually in a supplier's stockpile before signing a purchase order. In plain terms, asteroids come in different material types, and that type determines their value and how they'd need to be handled. The last core concept is why any of this gets studied or visited at all. Spacecraft missions travel to asteroids to collect samples, both to understand the early history of the solar system and to assess whether specific asteroids hold real resource value. This matters because it connects everything you've just learned to real engineering and investment decisions happening right now. Picture a home inspector examining the original materials used in a house's foundation before a buyer commits to purchasing it. The inspector isn't doing that out of curiosity. They're doing it because the original materials tell you what you're actually dealing with, and that information changes real decisions. Space agencies and companies study asteroids for the same reason. The samples tell you what you're actually working with, and that determines what happens next. Stated plainly, asteroids get studied and visited because their material tells us about the solar system's history and about what resources might actually be worth pursuing. Let me show you exactly how this works when several of these ideas come together on one real task. Picture a spacecraft company planning a mission to reach a specific asteroid and evaluate it for mining potential. First, the engineers confirm the real spacing of objects in the belt before mapping a flight path. Because the objects are spread out over huge distances, the path isn't a maze to be threaded through, it's mostly open space with occasional obstacles to track. Next, they calculate the target asteroid's specific orbital path and speed, because it isn't sitting still waiting for them. It's moving along its own elliptical route around the sun, and the timing of the mission has to account for exactly where that asteroid will be when the spacecraft arrives. Once they're closing in, they identify the asteroid's composition, rocky, metallic, or carbon-rich, because that determines whether the mission is even worth the cost and what kind of sampling equipment to bring. Finally, whatever data comes back doesn't just answer one question about one asteroid. It feeds into broader models of how the early solar system formed, which shapes which asteroid gets targeted next. In this single walkthrough, spacing, motion, composition, and the purpose of study all combine into one real decision, not four separate facts sitting next to each other. Here's what people most often get wrong, and it's worth being specific about each one. The first mistake is assuming the belt is a dense, crowded field, packed with rocks close enough to collide with constantly. This is easy to get wrong because visual media always exaggerates the spacing for dramatic effect, and that image sticks. The fix is to anchor yourself to the real distances involved, hundreds of thousands of miles between objects, not feet or yards. The second mistake is assuming all asteroids are made of the same material. This is easy to get wrong because they're all grouped under a single word, asteroid, which suggests uniformity that doesn't exist. The fix is to separate asteroids by composition type before drawing any conclusion about their value or risk. The third mistake is assuming the belt is fixed and static, like a ring painted on a diagram. This is easy to get wrong because most illustrations of the solar system show it as a still image rather than something in motion. The fix is to remember that every object in the belt is independently orbiting the sun at its own speed, all the time. The fourth mistake is assuming the belt would have become a planet if Jupiter simply wasn't there, as if removing one factor would have let the process finish on its own. This is easy to get wrong because it sounds like simple subtraction. The fix is understanding that Jupiter's gravity is an ongoing disruption across a very long time scale, not a single event that blocked one moment of planet formation. It has been acting on that material continuously since the solar system was young, which is a different kind of process than a single blocked step, and treating it as a one-time event leads to a wrong picture of how long-term physical processes actually work. Now let's look at where this understanding actually matters in your everyday life. If you read a news story about a company pursuing asteroid mining, understanding composition types lets you judge whether their claims about value are realistic, which can save you from putting money behind hype that doesn't hold up. If you watch an animation showing a spacecraft's route through the belt, understanding the real spacing means you won't misjudge the mission as reckless or nearly impossible, when in reality the path is mostly open space. If you come across news distinguishing near-Earth objects from asteroid belt objects, understanding independent orbits helps you tell an actual approaching risk apart from routine background activity, so you don't waste concern on the wrong thing or dismiss something that deserves attention. And if you're watching a movie or playing a game that shows a chaotic, wall-to-wall asteroid field, recognizing that as fiction keeps that exaggerated image from quietly becoming your baseline understanding of what space actually looks like. This same correction carries into practical conversations too. For example, if you're explaining to a coworker or a family member why an asteroid mining headline sounds more dramatic than it actually is, or why a spacecraft flying through the belt isn't the high-risk maneuver a movie trailer makes it look like. Having the accurate scale in your head lets you correct that kind of misunderstanding on the spot, instead of repeating the same wrong picture everyone else already has. You can now picture the asteroid belt at its real scale, spread out and mostly empty, instead of the dense field version most people carry around. You can explain why that region holds scattered debris instead of a planet, using Jupiter's ongoing gravitational influence as the actual reason. You can tell asteroids apart by composition and explain why that distinction changes their value and how they'd be handled. And you can look at a headline, a mining claim, or a space scene in a film and measure it against what's actually true instead of against what looks dramatic. This is the understanding you should have gotten the first time this topic ever came up. And now you have it.